Hey everyone, this is 8.2 interest. We're going to split this up into two pieces, essentially simple interest and compound interest. We're not going to talk about simple interest as much because it's a little simple, but simple interest is essentially interest that is earned on the principal only. So in general, we're either going to be investing some money or borrowing some money, and while we have that money invested or borrowed, we're either going to earn interest or end up paying some extra interest, which is basically the fee you pay to borrow money or the benefit you get for investing money. It's a percent of the money that you invest given over time. So the key here for simple interest is that interest is earned on the principal only. We'll see the difference in compound interest in a second when we talk about it, but these are the main two formulas we're going to use. I equals PRT, hopefully you're somewhat familiar with. Principal is the amount that you invest. Rate is the amount of time that, rate is the percent of interest that you earn back, your interest rate. And T is the amount of time that you leave it invested. This is what we sometimes just call the simple interest formula. This second formula, the future value of simple interest, this makes a lot of sense if you think about it, because usually, let's say you invest some principal P, you're going to earn the interest, which is literally just I, but you're also going to get back the money that you invested originally, which is P. That's literally what this formula says. It's P, the amount of money you invested, plus all of the interest that you got for investing. And so we just call that the future value of simple interest. Often you see this written differently. That's a 1 plus RT. This is just a simpler way to write the formula, but it actually means the same thing. Because if you just distribute this P through, P times 1 is P, P times RT is PRT. Right? So it really is the same formula. I just think it makes more sense for you to see it this way so that you understand it's not really a new formula. It's actually just the interest plus what you invested. It's a pretty formula that I think makes a lot of sense. So compound interest is what we're mainly going to talk about. And compound interest is interest that is earned not just on the principal, also the previous interest that you've earned. So let's say you're making some kind of monthly interest off of something you have in your savings account. So you put some money in your savings account, and that first month you get a tiny percentage of it back. Now the next month you're going to earn interest not just on the amount of money that you first had in the account. You're going to earn interest on that money plus the interest that you already earned. That's essentially compound interest. You're earning interest on interest, etc., etc. So we can compound interest a different number of times per year. We could do it once a year, which is actually what we saw in 7.4. We used the compound interest formula with M being 1, which I'll talk about in a second. But you can also compound interest monthly, quarterly, which is 4 times a year, daily, which is 365 times a year, and a variety of different ways. Those are kind of the main ones we're going to be working with. So this is the formula, and this is future value of compound interest. A equals P times 1 plus R over M, close your parentheses, raise it all to the n power. Now, before we talk about these pieces, kind of the main difference between this formula and the last formula, the future value of simple interest, is that n, which is standing for your time, is in the exponent. For simple interest, there are no exponents. So that's kind of like a key difference that also makes the arithmetic a little bit more complicated when you're using this formula. So you already know what A, P, and R are. Same thing as before. Future value, the principal, which is the amount that you originally borrow or invest. R is your interest rate. M is the number of times compounded per year. So like I said, if it's compounded yearly, that's just 1 time a year. M would be 1. If it's compounded quarterly, 4 times a year, that would be M would be 4. Monthly, M would be 12. And daily, M would literally be 365 because that's how many times it would be compounded per year. N, on the other hand, this is still standing for a time, but in the previous formula, T is almost always years because you usually have an annual interest and then years. Here, N is the number of compounding periods. What this essentially means is, up here, if M is 12, let's say you're compounded monthly, N is actually going to be in months. So you don't want to say, N is essentially time, but you don't want to think of N as years necessarily, right? It all depends on what type of compounding you're doing. So if you're compounding daily, then N would be in days. Compounding yearly, N would be in years. If you're compounding quarterly, N would be in quarters. Also, you can calculate N pretty easily by multiplying M times T. Here, T is standing for the number of years that you're investing in something, and M would be the number of times you're compounding it per year. So for example, if you're investing something for 5 years and it's compounded monthly, that would be 12 times a year, right? So 12 times 5 would give you N, that would give you 60 months. Alright, so we're going to do a problem on page 397, number 41. Notice in the italics above it says, assume the lender is using simple interest. Make sure you look for this in problems. It's sometimes simple interest, sometimes compound interest. Before you start thinking about what formula to use, figure out what type of interest you have. So most of the time we'll be using compound, but if it is simple interest, it'll say somewhere pretty obviously in the problem, so look out for that. This one says you plan to take a trip to the Grand Canyon in 2 years. You want to buy a certificate of deposit for $1,200 that you will cash in for your trip. What annual interest rate must you obtain on the certificate if you need $1,500 for your trip? Certificate of deposits, that's kind of a weird way to put it. I don't know exactly how this works. I've never done it, but essentially it's like when it says you're buying this for $1,200, imagine you're investing $1,200 in some account, right? You're investing in there, you're going to leave it in there for 2 years, and when we take it out, we want to have $1,500. So the question is, what interest rate are we going to have to earn on it before we take it out? So in this case, you kind of hold the certificate for 2 years. It increases in value by some interest rate, and when you cash it in, you get your $1,200 plus the interest that you earned. We want that to be $1,500. So this is simple interest, and since we have that $1,500 goal, that's our future amount we're after, it makes sense to just start with the future value of simple interest formula. I'm going to use this version just because, like I said, it's more common. So this is P times 1 plus RT. We have our A, it's 1,500, that's how much we want to have in the future. We have our P, it is 1,200, that's how much we are buying it for, it's essentially how much we're investing. T is 2 years, and R is what we're after, so I'm going to call this 2R. And then we'll be solving for R, which is our annual interest rate. Now, real quick, R and T over here, these are important because they both have units of time, and those units of time have to match. So they told us that we're going to take a trip in 2 years, so time has already been set in years. You have to make sure that your interest rate is also in years. Well, they said, what annual interest rate must you obtain? So that means R has to be yearly, which means it's okay that T is also in years. So basically, make sure these two things match. You'll see in the next problem, we'll have to kind of force one to match the other. But for now, we're good because this is in years and this is annual interest rate. So we want to just solve this for R. There's a couple ways we could do that too. Normally, we have to divide out the 1,200, but that's because we can't get inside these parentheses when there's an exponent here. Since simple interest doesn't have exponents, it's actually a little bit easier to solve. You could just take your 1,200 and distribute it through, essentially. So I'll show you that method. You actually would be fine if you divided it out too. But this is just some basic algebra, trying to get all our numbers on one side, all our variables on the other, and here we're just clearing parentheses. 1,200 times 1 is 1,200, and 1,200 times 2 is 2,400, with the R along for the ride. We want to get R by itself, so next we'll move this 1,200 to the other side. That gives us 300 equals 2,400 R. And then if we want to solve for R, divide both sides by 2,400. And then if you throw this in the calculator, you should get an R equal to 0.125. And then don't forget, R is an annual interest rate, so we need to write it as a percent at the end. So we'll call this 12.5%. Move your decimal twice to the right if you want to make it into a percent. So there we go. He's going to need a 12.5% interest rate on the certificate of deposit if he wants his $1,200 to turn into $1,500 within 2 years. Alright, same idea as the last one, same page. This is number 42. Jonathan wants to defer his payment of his $4,500 tax bill for 4 months. If he must pay an annual interest rate of 15% for doing this, what will his total payment be? So again, this is a case of simple interest. They tell us up in the italics it definitely is, but it's kind of a weird way of putting it here. He's deferring payment of his $4,500 tax bill. So it's kind of like he's borrowed that money right now because he can't pay it, and he's going to borrow it for 4 months, and then he has to pay it all off. But during those 4 months, he's going to pay an annual interest rate of 15%. And the question is, what will his future payment be? His total payment? Well, obviously it's going to be $4,500 because he already owes that, plus some interest, right? And that's exactly how our future value of simple interest works. It's the amount you originally owe, which in this case is going to be our P. That's our 4,500, plus the interest part. 15% is our interest rate. We have a time T. It's 4 months, and then we're going to basically just solve for A. Now, we have to be careful here, though, because we have a time of 4 months, but we want we have an annual interest rate of 15%. So right now our time units aren't matching. We have annual, which is yearly, and we have months. So we need to make them match, essentially. So, first let's plug in what we have. 4,500 is our original bill. That's the principal. And then 1 plus. Now for R, it's annual interest rate. It's 15%, so I'm just going to call it 0.15. And that is yearly. So what we're going to have to do is we're going to have to make our 4 months into years. So what is 4 months in terms of a year? Well, it's obviously less than a year. And in fact, it's 4/12ths of a year, right? Because there's 12 months and we have 4 months, so we have 4/12ths of a month. So you can literally just put that in there, 4/12. This is the same thing as 1/3, obviously, which is 0.3 repeated. But we'll just throw it all in the calculator and we'll just round it to the nearest cent anyways because this is money. So keep in mind, this is the only tricky thing that can really happen in simple interest. Make sure your interest rate and your time units are matching. This is annual interest rate, and 4 months is 4/12ths of a year. So this is now in years. Okay, so now we're just essentially crunching numbers. You can distribute the 4,500 through. Let me just see what I did real quick. Yeah, I just jumped to the answer, but I'll give you a couple steps here. So let's distribute 4,500. So we get 4,500 times 1, which is 4,500. Plus, this is actually the interest that we're going to end up having. So it'll be 4,500 times 0.15 times 4/12ths. And I got 225. That is the actual amount of interest we're going to end up paying. And then when you add this together, you should get 47.25. This is in money. And this is how much he's actually going to have to pay back since he's deferring his income taxes. This is a comma, not a decimal, sorry. Alright, last simple interest problem here on page 397, number 43. Sanjay has borrowed $400 on his father's watch from the Main Street pawn shop. He's agreed to pay off the loan with $425 1 month later. What is the annual interest rate that he is being charged? So he's borrowing 400. He's going to pay back 425. That's his future value, and he's going to pay it back in 1 month, which is our unit of time. The question is, what is the annual interest rate? So they want us to solve for R. Let's go ahead and start out with our future value. Oops, I messed up the formula. Future value of simple interest. There we go. We're going to pay off 425 in the future. We borrowed 400. And now interest rate is what we're after. It's annual again, and our time unit is once again in months. So we're going to have to turn our time unit into years. 1 month is 1/12th of a year. And then we'll multiply it by our interest rate. So again, we made sure to match our units. They wanted an annual interest rate, which is yearly. So we took our 1 month and we turned it into a year. It's 1/12th of a year. Okay, let's go ahead and solve this for R now. We could distribute the 400 through, doesn't really matter. I'm going to go ahead and just divide, just to show you can do it the other way too. Divide by 400, both sides. So you get 425 over 400 equals 1 plus 1/12 R. Now if you want to solve for R, you can subtract 1 from both sides. And since this is kind of calculator work, I'm going to save some of this work to the very end. so we don't get any rounding errors. So we currently have 425 over 400 minus 1 equals 1/12 r, right? Because our minus 1's canceled, or our 1's canceled out there. And then lastly, if you want to solve this for r, you can multiply both sides by 12. I'll fit it in right there. Right, because now 12, this is 12 over 1 essentially, it's going to cancel out with that 12 there and just leave you with 1r. So if you throw all this in the calculator, 425 over 400 minus 1, and then multiply it all by 12, you should get 0.75. Once again, they wanted an annual interest rate, so it better be a percent. R should be 75%. Which is pretty hardcore if you think about it, right? 75% interest rate. Notice, he's only borrowing for 1 month, right? But he's still paying $25, which is a pretty large chunk of the $400 that he started with. So 1 month of interest can actually be a ton of interest if you look at it in terms of what would the annual interest rate be. A comparable annual interest rate would be, well, in this case, it would be a full 75%. Alright, so we're going to jump into some compound interest now. So keep in mind this is going to have exponents, which is going to make things a little bit more complicated. So this is page 398, number 45. In the italics it says, Ann and Tom want to establish a fund for their grandson's college education. What lump sum must they deposit in each account in order to have $30,000 in the fund at the end of 15 years? It's compound interest. I guess they don't say it up there, but in 45 obviously they give us an interest rate, 6% annual, and they tell us that it's compounded quarterly. As soon as you see compound interest, at least in this section, you can go ahead and start with your compound interest formula. Very similar to the other formula except for the m and the n. So, what lump sum, the question up in the italics is what lump sum must they deposit? So in this problem, or in all these problems, 45 and 46 at least, they're asking for P, because P is the lump sum that you deposit, that's your principal, and then you earn interest on P. So they're asking us to solve for P. We want to have $30,000 in the future. That's obviously going to be our A. Right, because it says, what lump sum must they deposit, what is P, in order to have $30,000 in the fund, that is A, at the end of 15 years. Now, 15 is involved with our time, but got to be careful, it's not necessarily in. So let's look at the rest of this formula. We have 6% annual interest rate. That's pretty simple. We'll just put 0.06 for R. Don't forget to always turn it into a decimal. Now M is the number of times it's compounded per year. In 45 it tells us that we're compounded quarterly. Quarterly means you're compounded 4 times a year. So M is just going to be 4. Oops. And then lastly, our N is the number of compounding periods. That means if we're compounding 4 times a year for 15 years, N is going to be 4 times 15. It's essentially how many quarters there are in 15 years. So just so it's clear, I'll put the 4 times 15. So that's 4 times 15, not 4.15 by the way. Okay, so we want to solve this for P. What we're going to have to do is figure out what is this whole number here, and then we'll divide both sides by that number, and we'll get our P. So let's go ahead and, let's see. It's kind of not a lot to do before you throw it in the calculator. Let's go ahead and just divide by this number here. 1 plus 0.06 over 4, and I'm just going to call that 60, right? Don't forget these are both 60. Oops. Okay, and we'll divide that on this side. Okay, and you got to be careful, those cancel out by the way, you got to be careful here when you enter stuff like this in the calculator. What you basically want to do is make sure that the 30,000, make sure the numerators and denominators are nice and separate. So I'd start out with your 30,000 divided by, then open up a set of parentheses, then open up another set of parentheses and enter this whole thing, and then close your parentheses at the end, basically making sure that that whole piece is locked in the denominator. But if you throw that all into the calculator, you should get a number rounded to the nearest cent, something like 12,278.88. This is money, and that should be our P. Right, so if they want to have $30,000 in the end of at the end of 15 years with this all these constraints on this account, then they need to deposit $12,278.88. All right, so number 46, pretty much the same idea as last time. We have a different interest rate, and this time we're compounded monthly. Let's go ahead and start again with our formula. We still want to have $30,000 in the future. We're still solving for P. How much do they put in right now? R is this time going to be 0.075. Remember, decimal twice to the left. And since we're compounded monthly this time, M is going to be 12 because we're compounded 12 times a year, 12 months in a year. Also, N is going to be, we're compounded 12 times a year for 15 years, so it'll be 12 times 15. Okay. So just like last time, if you want to solve this for P, you're going to have to divide both sides by this whole thing in parentheses. 0.075, 12. 12 times 15 I have is 180. And same thing over here. So it cancels out here, and P is about equal to whatever you get out of this, which I got 9,773.73. Rounded to the nearest cent, and this is in money, in dollars. Alright, so notice how we kind of change the interest rate, change the compounding around. In this case, we earned more interest, and we were compounded more times a year, so it turns out we had to invest less money in order to have the $30,000 in 15 years. Usually, the more times it's compounded per year, the more money you get out of it, and kind of obviously, the higher the interest rate, the more money you get out of it as well. Okay, so another compound interest problem. It says, this is page 398, 56. Lucas purchased a bond with the face value of $10,000 for $4,200 to build a new sports stadium. If the bond pays 6.5% annual interest compounded monthly, how long must he hold it until it reaches full face value? You have to look in this problem until it says compounded monthly. That gives you a big hint as to what formula you're going to use, right? So obviously we are going to use our future value of compound interest. Notice the question is how long must he hold it? That means we're going to solve for n. And if you remember back to 7.4, that means we're going to end up using logarithms. So I'll remind you of that step when we get there. Let's see what we have. We have a bond with a face value of $10,000. We want to know how long until it reaches its face value. So the future value we're looking for is $10,000. We bought it for $4,200. That's our principal. We're basically investing that. We've got our 6.5 annual interest. Compounded monthly means 12 times a year. So let's go ahead and plug everything in. 10,000 for A. 4,200 for P. 6.5% would be 0.065. And compounded monthly means 12 times a year, over 12. Okay, and then N is what we're after. And we have to be careful about N, so let's just get N, and then we'll talk about units, right? Because N isn't years, remember, it's always the same number of things that you're being compounded by. So in this case, since we're compounded monthly, N will be in months. Okay, so let's say we want to solve this for N, though. We're definitely going to have to get rid of this 4,200 to start with. So we're going to divide it on both sides. Over here, let's not worry about the details, but I'll cancel out 2 zeros. So we'll just call it 100 over 42 for now. And then over here, yeah, you're not going to get a nice number out of this, so let's go ahead and just stick with what we have. Let me make some room real quick. Okay, so we have 100 over 42 equals, and then we have some number. There's our number, raised to a variable power. So if we want to get this variable by itself, we want to solve for it or get it out of the exponent, we are going to have to take a logarithm of both sides. So essentially you're going to apply a log of this side and then apply a log to this whole side. Just fit it in there. Alright, and the whole point is this exponent now is going to come down in front of the logarithm because we have that exponent property of log. So when that happens, this looks messy because I don't want to do anything in the calculator till the last step, but when that happens, what we have now is we have log of 100 over 42 equals n times, so that exponent came down, log of this whole mess. That right there. And this is just a number, so if we want to solve it for n, we can literally divide both sides by this logarithm, which is, again, just some number. Cancels out here, and our answer will be whatever we get out of throwing this whole thing in the calculator. Now, just like last time, this is actually a little bit easier because it's just a log divided by a log. Do log of, it'll open parentheses, 100 over 42, close it, divided by log of, open parentheses, and then you can pretty much enter that 1 plus 0.065 over 12, pretty much straightforward, and the order of operations should be fine. So I got n is about equal to 160.58 something. Oh, technically it would be 59, sorry. Now the problem is, well, this isn't really a problem because I don't think they specified how they want you to answer the problem, but my math labs is picky, so if the units here, these are actually in months right now. So sometimes they might want you to answer in years instead. So obviously if you have months and they want years, just divide it by 12. So if you divide this by 12, it's about 13.4 years. Right, so I don't really care what units you give me and just make sure they're correct, but my math labs will definitely say years or months, I think. So keep in mind, anytime you have to solve for n, since it's the exponent, you're going to end up using logarithms, just like we did in 7.4. Alright, so page 398, number 57. We have Allison is 30 years old and plans to retire at age 65 with $1,200,000 in her retirement account. What amount would she have to set aside now in an investment paying 6% annual interest if the compounding is done daily? Alright, so we know we have compound interest. We know we're going to end up using the future value of compound interest formula. They're asking us for what lump sum again, so we're solving for P. We know our A, it's going to be 1,200,000. Let's go ahead and plug that in. Oops. This is how much she wants to have in her retirement account in the future. Still solving for P. Annual interest is 6%, so that's 0.06. Now the compounding is done daily. So they said assume 365 days in a year. You can always assume that, by the way. So M will be 365. Remember, because it's compounded daily, it's compounded once a day, which is just 365 times a year. Now, what about N? Well, she's 30 years old. She wants to retire at age 65. That's 65 minus 30, which is obviously 35 years. Now, the problem is we're compounding daily, so our N is going to be actually in the number of days. So that'll be 35 years times 365 days. So 365 times 35 is actually our N here. So what we're going to do either way, we want to solve for P, so we're just going to divide by this whole number, the 1 plus 0.06 over 365. And if you multiply those two numbers out, by the way, I got 12,775. And this whole number is what we're dividing by over here. Sorry, I got a little messy there. Alright, it all cancels out here. P is about equal to whatever you get out of this, which I have to do still, so bear with me. Not 14, 146,973 round to the nearest cent, it would be in 8 cents. So that is the amount of money that you need to invest now, or she needs to invest now if she wants to retire in 35 years with $1,200,000 if she gets a retirement interest of 6% and the compounding is done daily. Alright, so that is pretty much all the problems I wanted to talk about. However, if you take a look at page 393, it'll show you a very, very useful application to use on your calculator. And the key to this is it only works with compound interest. And I'm actually going to write that because it's very important. Only works with compound interest. That is important. But the good news is anytime you have compound interest, essentially, you can use it. So all the problems in 8.2 that involve compound interest, not simple interest, by the way, not so much in 8.3, but pretty much all of 8.4 and all of 8.5, you can use this thing called the TVM solver. It means time value of money, so it essentially has to do all with kind of interest things. And it has all these pieces, and you can basically set up a problem, then throw all the values into this calculator application, and it will spit out the answer. So I have a separate video about this up in the video lecture section. So check it out. It's called the TVM solver examples, and it'll show you how to do this on a variety of different problems. So this will be your best friend. I want you to use it actually, and I want you to use it even on the exams because I think it's the fastest, most accurate way to get answers with the calculator, which you're going to use anyways, right? All of this is calculator work once you get it plugged into the formula and do kind of your basic algebra steps. So check out the TVM solver. Let me know if you have any questions, and keep up the good work.